The LM1875, an old power amplifier IC, but still a very rugged power amplifier IC. Greetings, the Astro 30 here, recovering from a cold, and today we're going to be looking at the old LM1875 power amplifier IC. Now this particular IC is capable of up to, according to the datasheet anyway, 30 watts, but they rounded off down to 20 watts at the recommended supply voltages into 8 ohms. And we're going to look at the data sheet in just a second. This particular IC has been around for donkey's years. I remember using one of these ICs back in 1997, somewhere around about there. So they've been around quite a while. It should say on the data sheet, with the copyright information anyway, of how old it is, but I'm pretty sure this goes back to the early 80s. But again, I'm not too sure on that. But it's a very useful IC. It requires very limited components around it to make it work. It's basically, for want of a better term, plug and play. So anyway, let's have a look at the datasheet. Okay, thank God for editing. That took longer than necessary. When I printed out the PDF, it wanted to print all the odd pages first, then print the even pages, then I had to sit there and sort out which page was which. Anyhow, this is the data sheet for the LM1875. It's stated as 20 watt audio power amplifier. Up to 30 watts output power. Average voltage output typically 90 decibels. Low distortion of 0.015%, which is at 1 kilohertz at the full power output of 20 watts. So its distortion is relatively low. It features a wide power bandwidth of 70 kilohertz. That's how much frequency it can amplify up to. Protection for AC and DC short circuits to ground. So if you short the output, you won't kill the IC. There's thermal protection with parole circuit. We won't worry too much about what that is. High current capability of 4 amps. Wide supply range of 16 volt to 60 volt. Now that would be from the positive rail to the negative rail. So in a bipolar power supply circuit, for instance, 16 volt would be plus minus 8 volt. And 60 volt will be plus minus 30 volt respectively. So they're measuring these voltages, or giving you these voltage ratings, as if you were measuring from the VCC line to the VEE line. So that's the total voltage, not the split rail voltage. So keep that in mind. Internal output protection diodes, 94 decibel ripple rejection, plastic package, TO220. Applications are high performance audio system, bridge amplifiers, so you can actually bridge them if you want to, stereo phonographs, servo amplifiers, instrument systems. Now in the description, the second paragraph says the LM1875 delivers 20 watts into a 4 or 8 ohm load on plus minus 25 volt supplies. Using an 8 ohm load and plus minus 30 volt supplies, over 30 watts of power may be delivered. Now, however, if you want to run this on either 4 or 8 ohm, then you would limit the supply to plus minus 25 volt. Because they can't guarantee at plus minus 30 volt the amplifier is going to remain stable into 4 ohm loads. So, considering most hi-fi equipment uses 6 to 8 ohm load speakers, it's not going to be an issue. 4 ohm is mostly to do with car audio, and I've rarely ever seen 4 ohm speakers used in a domestic hi-fi speaker. And there's their typical application circuit, which is the one I'm going to be using. It's a standard op-amp arrangement, if you like. There's not much to it. We've got feedback, network and gain set with these two resistors, the 20k and the 1k respectively. That gives us a gain of 21, which is gain equals resistive feedback divided by resistive gain plus 1, so that's 21. And in decibels, for anyone that's interested, and yes, I've got a new phone, if we use the log 20 law, so we go log the gain, which is 21, multiplied by 20, gives us 26.4 roughly decibels. So that's the gain in decibels, if anyone was interested. So there's not much really to talk about this particular application here. It's using a 1 mega ohm input impedance resistor here, and then a 22k ground reference resistor on this side. But other than that, it's not that exciting. Got 100 microfarad electrolytics here on both the supply lines to ground, plus 0.1 microfarad capacitors also on the supply lines for filtering the supply lines. And I would typically mount the 0.1 microfarads at least as close to the device as possible. They do give you a basic board layout at the back of this data sheet for reference. It's really neither here nor there. And they also give you a typical application for single supply operation. And now, from what I remember, the LM1875 from this circuit diagram from this data sheet, including the split supply version, I believe was in the data section at the back of the Dick Smith catalogue back in the day. So you didn't even really need to look up the data sheet. Now prepare to fall over on the floor. This is the equivalent schematic for the LM1875, and it looks fairly complicated. What? What the fuck? I'm not going to go too in-depth on this schematic. So this is their basic board layout for the split supply version. Albeit it's printed off because the components don't actually match where the pads are on the thing, so that the overlay is actually too far down this way compared to the copper traces. But as you can see, it's a pretty basic layout. There's nothing really to consider. This is the ground return, so every ground should return to a central point, as in all audio amplifiers. They even give over the page one for the single-ended supply. Again, it's up to you how you lay it out, but the data sheet is there for a reason, and they give you this information for a reason. You can follow it to AT to a point, but you don't have to be exactly that anal about it, because these little ICs are quite good at working even with the crappiest board layout. Trust me, I've seen some pretty crappy board layouts and they still seem to perform okay. So that's it for the data sheet. There's nothing much more interesting to go on in this thing. It just goes into package amendments and, you know, mechanical data for, you know, the actual IC itself, etc. And important notices like do not use these devices for life preserving medical equipment. So what we're going to do is we're going to take this little integrated circuit. I'm going to breadboard up the main application circuit here. I'm going to have to solder some fly leads onto the ends of the terminals here, because obviously this is not going to fit in the breadboard, and this is also going to have to mount to a heatsink. Never run a power amplifier, even an IC power amplifier, even just for testing, without it bolted to a heatsink, because you can destroy the chip or the amplifier pretty quickly. So I'm going to get busy doing that, and we're going to take some power measurements. Now I'm going to go from the minimum supply voltage of plus minus 8 volt to the maximum supply voltage of plus minus 30 and do some power measurements along the way and table them out and see what the results are. Okay, about half an hour later I've got the circuit all breadboarded out. I've checked it a few times. As messy as it looks, it's still functional. And this is the correct way to use this type of breadboard, with the power connections going in here and the fly wires are connected to these banana posts. That's how it's supposed to be wired. Now, before I get too excited, got the multimeter sitting there, I'm just going to do a quick output ohm check, because, well, if it's short-circuited, it's no good. And currently we're looking at 47 odd mega ohm and falling, so the output is not shorted. So now I'm going to stick the meter on the millivolt scale. I've got the power supply roughly at plus minus 8 volt to start with, and I've also got the current limiting knob down to around about, I think that's roughly about an amp. So we turn the load on and look for smoke. Well, no smoke, and the outputs come up to, got to wait for things to stabilize, but yeah, we're looking at, actually that would be 1.0 millivolt. So it was less than a millivolt. So the output is not outputting any DC, so it should be okay to assume that you can connect it to a speaker without damaging anything. And quiescent wise, the current draw is 40 mA, so that's not too bad. It would seem a little high considering that the amplifier isn't even driving a load, it's just powering the multimeter. Okay, so I know that it's not going to blow a speaker up, so what I'll do is, before I get excited with connecting it to an oscilloscope and doing some measurements, I will plug it into a speaker and just see if it makes a noise. Alright, got it hooked up to a speaker, turn the load back on, got a slight little click. Oh yes. That is definitely working as an amplifier. Okay, so let's hook it up to an oscilloscope and do some measurement tests. Okay, I've got everything set up. I'm doing all the tests at 1 kilohertz with the DDS at various different input sensitivity voltages, or output peak-to-peak voltages here. And they're all going to be tested into an 8 ohm dummy load. Got the oscilloscope set up there, currently at 1 kilohertz, 500 millivolt peak-to-peak in, so I turn the load on. I'm also using a ×10 probe, so we're looking at an output so far about 11.6 volt peak-to-peak. So what I'm going to do is I'm going to wind the amplitude up until it clips, and it's going to probably clip pretty badly considering it's on very low voltage. So it's 600 millivolt, 700, and it's starting to clip. So we'll ballpark that at 600 millivolt. And once that stabilizes, we're looking at a current draw of 450 milliamps. So at 600 millivolts we're pushing about 13.1 volt peak to peak. So what's that in power? Now obviously I could use the computer's calculator, but divide that by 2 is 6.55, multiply that by itself, and this phone still does not allow you to go 6.55 multiplied equals to get squaring, which is annoying. So that's 42.9, and we divide that by our resistive load. We're currently getting about 5.36 watts. Not very significant. So now what I'll do is, off camera, I will increase the supply voltage. I'm not going to go too anal about it. Probably do it in increments of, I don't know, 4 volt or so. That's plus minus 4 volt, so 8 volt total. And then work out what the input sensitivity versus the power output, and then come back with a table of results. Okay, well I've done the tests and I'm actually quite surprised at the results. I was expecting a lot less. The only issue was I went up to plus minus 25 volt and that IC is getting red hot. That IC was getting hot. I've turned the input voltage down, and I've also turned the input coming off the frequency generator down. I might stick that back up to 25 plus minus and just see if it's the supply voltage doing it or whether it was the amount of input going into it. 24.3 should do. Just doing a quick heat test here. Yeah, no, it should be right at plus minus 25 volt. It's just that when it starts amplifying quite significantly, it gets hot, quite hot. Anyway, on to our tests. We had a set supply voltage, and we end up with a set sensitivity or input sensitivity. That's what sensitivity means. At 16 volt, which is the minimum, we're getting 5.3 watt, 450 mA current draw with a 600 millivolt peak-to-peak input signal. Now that's, if you divide these voltages in half, that gives you the split supply rail voltages respectively, so that's plus minus 8 volt. At 20 volt or plus minus 10 volt, we're getting 7.6 watts, 540 milliamp current draw with a 700 millivolt peak-to-peak input. Now this is all before clipping. At plus minus 12 volt, we're getting 14.1 watt, 700 milliamp current draw with a input sensitivity of 1 volt peak-to-peak. At plus minus 14 volt, we're getting 14.1 watt, 770 milliamps, and a input sensitivity is still around 1 volt peak-to-peak. Now I went in increments of 4 volts here. At plus minus 16 volt, we've got 16.8 watts at 820 milliamps current draw with an input sensitivity of 1.1 volt peak-to-peak. At a input voltage of plus minus 18, we've got 23.8 watts at 1.06 amp current draw, 1.3 volt peak-to-peak input sensitivity. At a input voltage of plus minus 20, we're getting a whopping 30.6 watts at 1.18 amps current draw at an input sensitivity of 1.5 volt peak-to-peak. And at what I want to call the absolute maximum, which is plus minus 25 volt, we're getting a whopping 55.1 watts with a current draw of 1.3 amps with an input sensitivity of 2 volt peak-to-peak. Now that's quite significant and quite impressive at the same time. However, the device will get quite hot at those higher ratings, and remember the output in watts here is the peak value, what its instantaneous peak is. What its RMS value would be a lot less, but I don't deal with watts RMS because, well, it's kind of a meaningless unit of measure in the audio world anyway. So we'll just stick to the peak output powers, which is capable of at least 55 watt in my opinion. Okay, so now we want to do a sweep test on this amplifier.
That was a joke. I'm glad you told me.
No, I'm joking. Put him up there. Do a proper frequency sweep test on the amplifier, so I'll go into our sweep mode. Maybe sometime today. There we go. I'm back in ×1 probe here. From a sweep point of 20 Hz to 20 kHz, it looks reasonably flat. The voltage is not dropping off that significantly. So the frequency response of the amplifier is pretty good over the audio spectrum range. So now, having done that, I can kill the DDS and we can actually hook this up to a speaker and an input source. I'll just use the laptop because it's convenient, and just output some sound to a speaker and see what it sounds like. Suck my dick. Suck my fucking dick. Suck my fucking dick. Don't mind me, I'm just waiting for shit to load. Might as well have a smoke in the interim whilst I'm waiting for that. Maybe this will help. Well, nothing appeared to happen, so let's try clicking it again. Oh, come on. Oh shit, now my lead popped off. I suppose it really matters where the ground goes. I'll put it on this one. Stay on there. Okay, and now that I've got the YouTube audio library up, I can turn the supply on and actually play a track and see what it sounds like. Finally. Yeah. Sounds like I've got distortion. Okay, so I'm going to swap speakers real quick because that sounds distorted. Nope, still got distortion there. Penis. Albeit there was distortion, or there is distortion. It doesn't seem to distort there. Yeah. So, yeah, I'm not too sure where to assess that at. But yeah, there was significant distortion on the input. Now I'm not sure whether that was because of the circuitry there or whether it's something to do with the laptop, but it shouldn't be distorted that bad. I mean, we weren't even pushing probably 5-10 watts there, and it shouldn't have been distorted. This distortion has got me a bit perplexed. It shouldn't be distorting. So I don't know. Okay, so I've wired up a second LM1875 TIC there. I always buy two in case I damage one, and I noticed with this one the print's starting to fade as it was getting really hot when I was touching it, which is kind of suspect. The print shouldn't be coming off, and the print's brighter on that one. They're both from the same batch, so it's anyone's guess. I'll turn the supply on. Nothing unusual happened. Oh, that was the fridge compressor turning off. I wonder what that pop was. Really? Well, that's interesting. This one's actually drawing 60 mA too, by the way. No, there's still distortion there. So, I don't know what to actually make of that, whether it's the circuit layout or these wires might have something to do with it, interfering with it, or extra added capacitance or some crap, but yeah, that's unusual for it to be distorted at that low level. It shouldn't be doing that. It could be that these ICs, even though they came from JCar, they could be counterfeit. It's very possible. It is an old IC and it's remanufactured by Chinese people now, and it does have the National Semiconductor logo on the device, but that does not mean to say that it is actually from National Semiconductor. Well, that was disappointing. That was so underwhelming. It was more underwhelming than my first kiss. I took the laptop out of the equation. I connected the input of the amplifier up to the output of the CD player through this potentiometer here as a volume control, and there's very little to no distortion now. Wonder why? So I'll just go back a track. Ignore the guitar being distorted. Now that sounds a shitload better than it did, so I'm just going to find another disc. Well, there doesn't seem to be much wrong with the audio output of the amplifier. That track's a bit heavily compressed. Yeah, so I wanted to end this video on a bit of a high. There doesn't appear to be anything wrong with the LM1875T chips that I've got. Now, that first track had a little bit of over compression, but I couldn't hear any distortion in that track or even this track, and if you can, you're doing better than I am. But I haven't done any modifications to the circuit other than adding the volume pot there, but I did change the 22 mica electrolytic there to a bipolar cap, makes no difference. Yeah, and it's working fine, and I can't fault it now. And remember, both of these ICs were doing the same thing, or exhibiting the same effects on the laptop. So there is nothing absolutely wrong with these ICs that I can detect now. Because what was strange, let's turn that down a bit further. So the thing that was odd was that I was getting a great signal output on the oscilloscope with pretty high power before clipping. But then when I put it onto the music source, it just sounded crap. And I couldn't figure out as to why. So I've taken the laptop out of the equation, hooked it up to a CD player and confirmed that yes, it's something to do with the output of the laptop is doing something funky to the input circuitry of the power amplifier. Could be an impedance mismatch there too. It really should be going through a preamplifier first before going into the power amp, but I've just proved that there is nothing wrong with these ICs, because I was a little bit disappointed. So yeah, well, I fixed it now. Not that I actually fixed it, but it's working properly now, as it should be. So I suppose the next burning question is, before I go, what am I going to do with this? Well, I plan to route out a PCB for it and make a 2-channel stereo amplifier here, just because I can. So it should work out quite small. But remember, with any amplifier, you can never have too big of a heatsink. You can always have too little heatsinking, but you can never have a heatsink that's too big. Anyway, I'm going to end this video again. This is the Astro 30 saying thanks for watching, and if you enjoyed this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyhow, this is the Astro 30 saying see ya, have a great day, and happy Class AB amplifier ICs.